Hi, I'm Hayden, and this is Zach, and today we want to show you the all-new USRP X440. This new software-defined radio is the widest bandwidth, highest channel density USRP yet. With 8 transmit channels and 8 receive channels and 1.6 gigahertz of instantaneous bandwidth, it's got a lot of capability packed into it. Being a direct sampled architecture, we're able to achieve full phase coherence across all 8 channels. So we have a nice demo here. Zach, you want to show us the phase coherence performance in action?
Sure, Hayden. So what we're looking at here is our hardware, our X440. As you can see, it's hooked up to a splitter, 1 transmit, and 8 receive channels. So we can actually map out the coherency between channels. Switching to the software, we can actually see the drift over time in the top graph. So all 8 channels, you can see the tightness of the line over time. That's your phase drift. The bottom left chart is showing the offset between each channel at runtime. And then the bottom right is showing the average skew over time, and then the standard deviation of the skew, where the standard deviation is the tightness of the phase. So pretty small.
Yeah, so I mean, I guess here, as we're looking at this, smaller is better, that those lines aren't moving relative to each other is very good. So we have some pretty good, channel-to-channel phase coherency performance. And that's really important for certain applications like direction finding, direction of arrival type applications, and can be useful for prototyping new algorithms and new waveforms in radar and electronic warfare, typically like things like counter-drone applications. This will be very, very useful for. So in addition to the multiple channel phase coherent performance of this radio, it also has a lot of bandwidth. So Zach, can you give us a demonstration of the using that full 1.6 gigahertz, of bandwidth performance on the radio?
Sure, Hayden. Let me switch to the next demo. So what we're looking at here is our X440. We are now just transmitting on 1 channel and receiving on 1 receiver. And we're doing that at approximately 1.6 gigahertz of bandwidth. What we're showing here is a wideband OFDM 5G signal. There are 8 subcarriers contained within, all 100 megahertz each. This is an extreme situation, just showcasing the wide bandwidth that the X440 is capable of doing.
So that would be a lot of data transfer for kind of a communications application. Another way people are using this radio is for prototyping radar applications. So being 1.6 gigahertz, it's really nice to be able to tune quickly within that bandwidth. So can you give us an example of a frequency hopping radar type application?
Of course. Let me just switch to the next demo. What we're looking at here is a radar emulated signal where it is hopping across the spectrum, which you can see on the top graph there, across that 1.6 gigahertz approximately. And on the bottom, you can see the randomness of the frequency hops in that waterfall plot.
So that's pretty cool. So you're able to you rapidly tune within that bandwidth, almost instantaneously, and that allows, engineers to prototype novel waveforms for things like, AI-driven or cognitive radar and electronic warfare type applications where you're emulating certain threats to, be able to either prototype or test certain assets with this, type of capability. So I appreciate the demo, Zach. There's a lot of capability packed into this little radio, and we're excited to see what people are going to use it for. So if you all want to learn more about USRPs, go to ni.com/USRP or edis.com. I appreciate your time.